All right, we're going to launch now into how to graph out motion and what exactly that looks like. And we're going to go through parts of a motion graph relatively fast, trying to get to using motion graphs. So here I have what a position time, this is all position time graphs, of an object that is stopped. So notice that it's staying at the exact same position, maybe 2 meters, as time continues to tick on. So it's going to be a flat line. On the other hand, if we're moving at a positive constant velocity, then we are increasing our displacement at a constant rate. So as time ticks along, we are increasing our displacement constantly. Thus, it's going to be a line or linear. If we're going at a negative constant velocity, then we are reducing our displacement, or excuse me, our position. So we are bringing it back down constantly as time ticks on. And these graphs, by the way, can occur above, and all of these can occur above and below the x-axis. That does not matter. Okay. Let's see, positive acceleration. As time ticks on, we begin to accelerate, which means we cover more and more ground as we go. So it's an exponential process. Deceleration is exponential also, just the other way, because we slow down, we decrease our position as time goes exponentially. Negative acceleration, we are accelerating back down, so exponentially increasing or exponentially decreasing our position, coming back down. Negative deceleration, we are exponentially trying to slow back down, or we are exponentially changing our position back down to a flat or a stopped. Now, whenever you're trying to remember these, just think about what's actually occurring. Whenever you accelerate, you're trying to speed up to eventually launch into a constant velocity. So your curve launches into a constant velocity. In deceleration, you're trying to slow down into a stopped position, right? So you can find that up on the graphs up here. Another thing that I want to point out is how identical negative acceleration and positive deceleration are, and the vice versa, negative deceleration, positive acceleration. Mathematically, they are part of the exact same parabola. So check out what happens whenever I draw in a negative acceleration graph onto a positive deceleration graph. It's the exact same parabola, just the other half of it. Same thing with the negative deceleration and positive acceleration. So it's the exact same thing. Thus, we talk about all of these just in terms of acceleration. Let me give a couple of examples of these that might help you understand why they're the same. Imagine throwing a ball directly up in the air. Gravity decelerates the ball down to a stop, but it doesn't actually remain stopped. It immediately starts to accelerate back down, negative acceleration. So a positive deceleration going up still, if we're going to call up positive, slowing down to a stop, and then accelerating back down. Likewise, imagine instead this time, and this will feel a little odd, your car is going backwards in reverse, and you've already built up some constant velocity there, but instead of applying the brakes, you put the car in drive, and for some odd reason the transmission of the car doesn't fall out from underneath, but you put the car in drive and you hit the gas, and so the tires start spinning forward while your car is still traveling backwards. Well, that's going to cause you to slow down, right? To decelerate down, you're going backwards, but you're slowing down, and eventually you'll stop, and your tires are still spinning forward, so then you'll start to accelerate back going the forward or the positive direction. All right, let's look at velocity time graphs now. If you are stopped, that means you have zero velocity, thus you're on the x-axis there in a velocity time graph, so as time ticks along, you still have zero velocity. If you have a positive constant velocity, that means you're going to have a flat line up at some positive number, maybe positive 2 here, so as time ticks along, you are holding flat line at positive 2 meters per second. Negative constant velocity, a flat line at some negative number, so below the x-axis. I should point out, whenever it came to velocities and things like that in position graphs, it didn't matter. Here, where you are in relation to the x-axis does matter, because we're going to have negative velocities on bottom and positive velocities up at the top. Velocity graph or acceleration. Acceleration, you are increasing your velocity in a linear manner. So as time goes along, if it's constant acceleration, your velocity is increasing linearly. Thus, also, if you are decelerating, positive deceleration, you're bringing your velocity back down to, if you're trying to come to a rest, back down to 0. Negative acceleration, coming down below the x-axis. Negative deceleration, coming back above the x-axis. And let me once again show you that these are actually, that negative acceleration and positive deceleration are the same thing, because if I took my negative acceleration line and I just kept drawing it down below the x-axis, you'd see it's mathematically the exact same, it's the exact same line. Right? Same thing for positive acceleration and negative deceleration if I brought this piece here and slid it over there. So positive acceleration, negative deceleration, same thing. Now acceleration time graphs, those are pretty boring if you deal with constant acceleration. We're going to get into one scenario where it isn't constant in this unit, but for the most part we only are going to live in constant acceleration terms. So your acceleration is either 0, and whenever you have 0 acceleration, that could mean you are stopped. Could also mean you're traveling at some positive or negative constant velocity, right? But one way or another, you're not accelerating. If you have a positive acceleration, you're up above, right? Or a negative deceleration. That's still a positive acceleration, so some line above the x-axis, it's some number, positive 2, let's say, and a negative acceleration, so you're speeding up backwards, if you will, or a positive deceleration, you are going forward, but you're trying to slow down. That's the same thing as a negative acceleration. That's a line below the x-axis. All right, I want to take a very simple story and actually sketch out a motion graph, velocity time and displacement time, position time, motion graph, just because I find sometimes whenever we do that, it helps the understanding of the different pieces and what they mean. So we're going to drive to Chick-fil-A for dinner, and so a person gets in their car and they accelerate off at a constant into a constant velocity, because that's what happens. You get in the car and you push the gas and you increase your speed. That's called acceleration. So in my position time graph, positive acceleration is a curve up like that into a constant velocity. So now I'm at a constant velocity, a flat line. Notice how, though, everything is smooth. That is critical, that everything be smooth. So we curve up, accelerating into a constant velocity. If there were any sharp points in a position time graph, that would actually require an infinite acceleration, because you would be changing your velocity instantaneously. So with a position time graph, please make sure that you use curves. You have accelerations in it, like here's an acceleration to a constant velocity, and then the next step is the guy gets to Chick-fil-A, he decelerates to a stop. Right, and so he's going to stay, according to the problem, at Chick-fil-A for quite a while, so I'm going to leave him stopped up there at Chick-fil-A. So, Chick-fil-A is somewhere up here, CFA. And then it says he's going to return home, so he's going to accelerate back home. Now, home is at position 0, right? So home's down here, so he's going to come back down. Negative acceleration into a constant velocity. So here was my curve down from my negative acceleration into a constant velocity, and then decelerating into a stop. Velocity time graph, that would look something like this. We would have him accelerating into a constant velocity, which he holds for a while until he decelerates to a stop. Right, and he stays stopped at Chick-fil-A for a good while. And I apologize that the position time graph and the velocity time graph don't perfectly line up here. He stays stopped for a long time until he's going to come back home. Now he's going to negatively accelerate, which is down below the x-axis, because he's coming with a negative velocity. We're choosing back towards home to be negative, right? If we were talking about graphically here, up is positive, down is negative on the position time graph. So towards Chick-fil-A is positive, back away from Chick-fil-A is negative. So he's coming back away from Chick-fil-A, negative acceleration, negative constant velocity until he reaches home, where he decelerates to a stop. Now in a velocity time graph, if your accelerations are constant, you will have sharp points, okay? Because you can change your velocity immediately as long as your acceleration is constant. So what's happening here is you're having a constant, you're changing your acceleration at these points. And what I just said previously there about changing velocity instantaneously, what these sharp points are showing you is that you're changing your acceleration instantaneously, which, while it technically does not happen, is an assumption we will have to make in this class to live in our constant acceleration world, where we have a positive acceleration and then immediately drops to 0, and then a negative acceleration, which then once again drops to 0. Here's another type of problem you could be given where you're given one of the three graphs. So this time I'm given a position time graph, and in this one I'm given a velocity time graph. And based upon one of those graphs, you're asked to sketch out, draw the velocity time and acceleration time graph, or the other two that aren't there. My recommendation whenever you are given this type of problem is to start out going through and labeling the graph that you are given. All right, so I went through and I labeled this one. Notice that whenever we come into a negative position, in other words, we're past the starting point and going past it in the other direction, if you will, it's still negative constant velocity. The negative depends upon which direction you're going. So it's still going further down, so it's still negative constant velocity. Positive constant velocity, because even though we're underneath the x-axis, we are going back the positive direction, back up there. So now I'm going to use these pieces and translate them into a velocity time graph, trying to keep everything lined up to the best of my ability. I will also point out this graph technically is not allowed because there are sharp points in a position time graph, but you will see that happen occasionally whenever we're just trying to get the concepts of translating one graph to another, just for making it easier. All right, so we start out with some positive constant velocity, and then we immediately drop down to a stop. Now, technically, we would need an acceleration piece. We wouldn't be able to immediately drop down like this, but we drop down to a stop. Then we're going to go to a negative constant velocity, so some negative constant velocity for a while, and then we come back up to a stop here. We stay stopped. Negative constant velocity again, it says. So I got to go negative constant velocity, having to drop straight down. Negative constant velocity, back to stopped. And then we have a positive constant velocity. Comes over and back down to a stop. Now notice whenever this is occurring, we don't care what position the velocities are happening at. We don't care that this negative constant velocity is at some position above the x-axis, some positive position, and this negative constant velocity is somewhere below the x-axis, some number behind where the person started out. Position no longer matters in a velocity time graph. Also, this probably would have been better if I had drawn this as a piecewise graph where I left that open and then I put a hole there and I actually filled that one in and didn't actually connect them. Likewise, you leave this open and put this here, not connect them, and so forth and so on. All right, so I fixed this into a proper piecewise graph. Now, with open on one end and closed on the other, just for just to make sure that it all lines up mathematically. Now, acceleration time graph. There is no acceleration happening in here, which is why it's improper. We're going from constant velocity to an immediate stop, which would require an infinite acceleration for that to occur. There's no accelerations being shown in this. So an acceleration time graph is actually very easy here. It's just zero the entire time. All right, so let's work on this other piece over here, these other graphs. I'm going to quickly label everything. Got positive constant velocity, positive deceleration, and negative acceleration. Notice how it's all part of the same line. It doesn't really matter. Those two pieces are the same. I have some negative constant velocity down here, and then a negative deceleration, which is the same thing as a positive acceleration, and then I am stopped right here. So now using these pieces, I think I'm going to go ahead and do the acceleration time graph first, just because, why not? So I have a positive constant velocity. Well, constant velocity is zero acceleration. Then I'm going to have a positive deceleration and a negative acceleration. Those are all the same thing. It's a negative acceleration, so piecewise graph here. For a chunk, I am accelerating negatively until I come back and I am going some negative constant velocity. Well, that's zero acceleration. You're never accelerating during constant velocity. Now I have a negative deceleration, which is once again a positive acceleration. Look at where the line's going. It's trying to go back up, right? And so you're accelerating back positively. So that's going to be up here, right, for a chunk of time until I come to a stop. And whenever we are stopped, we are actually at zero acceleration. All right, now I need to create my position time graph. I start out going at some constant velocity until I decelerate, so I'm going to start curving down, but I don't decelerate into a stop. I immediately decelerate into a negative acceleration. Think of a ball going up in the air and then, a ball thrown with some initial velocity and then curving back down into some negative acceleration into a constant velocity for a while. Right, and so I come down constant velocity all the way over here. Now I'm going to have a negative deceleration into a stop. So now I'm going to curve this off all the way into a stop. Let me go through and label that for you so maybe it's a little bit easier to see. All right, so there you go. All I'm doing here is I'm taking this piece and matching it up, and I'm trying to keep them as lined up to the best of my ability. Once again, I'm not ever going to be perfect with that, but trying to keep my constant velocity pieces lined up because everything's happening at the exact same time. At 2 seconds, what's happening at one graph has to be happening at 2 seconds on the other.